If Planet 9 really exists, why haven't we found it yet? The answer lies in a perfect storm of cosmic challenges. Challenges so subtle and stubborn that they've kept this potential giant hidden from our view for decades. First, there's the issue of brightness. Planet 9, if it exists, is believed to orbit at an average distance of 600 to 1,000 astronomical units, AU, from the Sun. That's 600 to 1,000 times farther than Earth. At such an extreme distance, even a massive planet, 5 to 10 times the mass of Earth, would receive almost no sunlight. And what little light it does receive, it would reflect only faintly. Depending on its surface and atmosphere, Planet 9 could be hundreds to thousands of times dimmer than Pluto. To even detect it, astronomers would need long-exposure images taken under optimal conditions with highly sensitive instruments. But brightness is only half the problem. The other issue? Movement, or rather, the lack of it. Because Planet 9 is so distant, it would take approximately 15,000 to 20,000 years to complete a single orbit around the Sun. That means its motion across the sky is incredibly slow, barely perceptible over days or even weeks. Why does that matter? Because the most common method astronomers use to detect new solar system objects is motion tracking. Telescopes take repeated images of the same region, hours or days apart. Anything that shifts position between frames, a small moving dot against the background stars, is flagged for analysis. That's how Pluto was discovered in 1930. Clyde Tombaugh spotted a tiny speck slowly shifting its place over the course of several nights. But Planet 9 wouldn't move like that. Not even close. To our telescopes, Planet 9 would appear nearly stationary, just another faint dot among the stars. Unless astronomers return to that same patch of sky again and again over months or even years, they might never notice its subtle drift. And here's the problem. Most telescope surveys aren't designed for that kind of persistence. Observatories operate on strict schedules, often with competing priorities. Time on the world's most powerful telescopes is precious. Astronomers have to apply for observing slots, and only a small fraction of projects get approved. That makes it hard to dedicate months of telescope time just to watch one spot. Even worse, we don't know exactly where to look. Planet 9 could be anywhere along a vast orbital path covering a huge swath of sky. Searching it all would be like scanning a desert for a grain of sand. Only the sand is moving so slowly it's nearly invisible. And then there's interference. Some parts of the sky, like the galactic plane, are filled with countless stars, gas clouds, and background noise. A faint, slow-moving object could easily get lost in that clutter, even if it's right in front of us. All these factors combine to make Planet 9 a master of cosmic hide-and-seek. But astronomers aren't giving up. New approaches are being developed, some involving AI-powered algorithms trained to detect ultra-slow motion. Others rely on comparing archival images taken years apart to identify tiny shifts. And future telescopes, like the Vera C. Rubin Observatory, are being built with wide-field, high-resolution surveys in mind. Even amateur astronomers are joining the hunt, combing through public data from space telescopes like WISE and Pan-STARRS, hoping to be the first to glimpse the elusive planet. It's a global effort, fueled by curiosity, data, and the drive to uncover one of the greatest cosmic secrets of our time. And the truth is, we may already have photographed Planet 9. We just haven't recognized it yet. Somewhere in a digital archive, in a quiet data center on Earth, a few pixels may already hold the proof we've been chasing for decades. All we need is the right eye to see it.